Welcome everybody to Probability and Analysis webinar. Today our speaker is Shivam Nadimpali from Columbia University, who is going to talk about testing convex truncation. Please, Shivam, feel free to start.
Awesome. All right. Thanks, Pata, for the invitation, and thank you all for coming. So I'll be talking about some joint work with Anindya Day, who's at UPenn, and my advisor, Rocco Servedio. And it's about testing convex truncation. The talk is 45 minutes long, so please stop me and ask me questions. Let's make this as interactive as possible. I can't see people, so feel free to unmute yourself and ask questions. That's completely okay. And I can see the chat, so if something's in the chat, I can respond. So let's get started. So this talk is about testing convex truncation, and it's actually a direct sequel to a talk that my advisor Rocco gave at this very seminar last fall about convex influences and a Gaussian correlation inequality, and a quantitative Gaussian correlation inequality. And my talk picks up exactly where his talk ends. So if you like my talk, or if you want to see more of this stuff, you can also watch Rocco's talk, and it's on YouTube. So coming to the title of my talk, it's about testing convex truncation, and in particular, it's going to be about truncated statistics, like the title suggests. So this is a super well-studied, super well-established field, dating all the way back to luminaries like Bernoulli, Galton, and Pearson. And informally, it kind of deals with distributions where some kind of truncation has taken place. So just as a concrete example, the red curve over here is the standard Gaussian distribution. And the green curve is just the density of a truncated one-dimensional Gaussian. So, everything beyond this vertical dotted line is the density to the right of this dotted line is set to 0, and you renormalize the density so that everything integrates to 1. And this is not just a well-studied, this wasn't just a field that was studied back in the 17, 18, and 1900s. It's still kind of a very active area. And, there's book-length monographs being written about this field even, in the past 5 years. And here are some examples. So the focus of this talk, as opposed to the one-dimensional picture I gave, the focus of this talk is going to be in the high-dimensional setting. So we're going to be thinking about probability distributions of Rn, where n is large. So think of n as going to infinity. And in particular, we will only be thinking about one probability distribution, which is the standard Gaussian distribution. So we all know the Gaussian, we love it. It's a rotationally invariant distribution. Everyone, it's a very natural probability distribution. Right? So just to make sense of the title, so let me kind of give you an example of what I mean by a truncated distribution. So on the left is a draw of 1,000 samples from the two-dimensional standard Gaussian distribution. And on the right is a draw of 1,000 samples from a truncated Gaussian. So what I mean by this is I'm drawing 1,000 samples from the Gaussian conditioned on this simple geometric convex body, since it's a simple convex body, which is just a slab. And the notation I'll be using throughout this talk is the following. I'm going to write N0IN for the Gaussian distribution, and I'm going to put a vertical bar and write K underneath the vertical bar to indicate that I'm drawing from the Gaussian conditioned on a convex set K. So in this picture, this purple slab is the convex set K. And maybe the most natural question to ask, when you think about truncated statistics is if you can even detect truncation. So the most natural question to ask is the following. You're given sample access to one of two possible distributions, either the standard Gaussian distribution in n dimensions, or the standard Gaussian distribution conditioned on some unknown set. And you want to figure out how many samples you need to distinguish between these two cases. Okay, so you're promised that the distribution you're getting samples from is one of these two, is either the Gaussian or the Gaussian conditioned on some set, and you want to distinguish between these. And this is a natural and clean question, but it's also ill-posed. It's not a well-posed question. And let me convince you of this with two simple examples. So here's 3 draws of 1,000 samples from of 1,000 samples from some distribution. And I'm promising you that 2 of these distributions are the Gaussian distribution, and the third one is not. And I know we're being recorded, but does anyone want to be bold enough to guess which one is the truncated distribution?
Maybe middle one.
Awesome. So Pada is exactly right. Pada, do you wanna say what you think the set is?
I think on the left, it looks like there is. I kind of see some boundary of the convex set, maybe.
Okay. Well, it's actually on the right. So the set I'm drawing from is this purple region. It obviously goes up to infinity, but in all directions. But all I did was I deleted a tiny part of the of space. Like I'm rejecting this thin white strip on the right side. And this naturally poses an issue, right? Like you want to delete a reasonable amount of mass, otherwise you will never be able to detect truncation. Like you could delete a set of measure 0 and it's just not well posed. So the first issue is that the
Sorry, but didn't you say convex bodies?
Oh, I'll come to that in 1 second. So right now I'm saying any
Okay.
yeah.
Okay.
Point here. So yeah, so I'm trying to convince you why you need the assumption of convexity. Great. So the issue with this picture right now is that you've deleted a tiny amount of mass, or in other words, the Gaussian measure of the set you're drawing samples from is really close to 1. So just to set up some notation, I'm going to write vol k, and I'll be calling it the volume of the set k to just mean the Gaussian measure of the set k. So just the probability that a standard Gaussian lands in the set k. And so the issue here is that the volume of the set k is really close to 1. So let's fix that. Let's say that now you're getting samples from either the Gaussian conditioned on a set whose volume is at most 0.8. So I'm promising you that I'm deleting 20% of Gaussian space. And here's another round of spot the truncation, 2 from the standard Gaussian and 1 from Gaussian conditioned on a set of volume at most 0.8. Pata, do you want to try again?
I would say again middle one.
Okay, so this time it's actually the one on the right. And let's zoom in. And it's a, as I think Shabarish suggested, like the issue over here is going to be the fact that the set you're drawing from is completely bizarre. Like it's not a convex set. It's like, a block of Swiss cheese where you've just randomly deleted chunks of Gaussian space. And it's kind of hopeless to detect any sort of truncation when the set lacks any structure. So like the picture suggests, I'm deleting a good amount of mass, but it's deleted in a very haphazard, in a very unstructured way. So this is another issue that we have to handle. And with these 2 issues in mind, we arrive at a very natural question with some additional quantifiers, which is the following. So you're given sample access to either the Gaussian or the Gaussian conditioned on some censoring set, where you're promised that the volume of the set is at most 1 minus epsilon. So think of epsilon as some fixed constant, 0.1, 0.2, favorite number, between 0 and 1. And we're also requiring that the set K is convex. So again, when you're thinking in high dimensions, convexity is the simplest geometric condition you could enforce on a set. So it's a very reasonable, very natural assumption to make. And we're asking, well, how many samples do you need to distinguish between these 2 cases? And we're going to be measuring progress as a function of the dimension n and epsilon. So we want to use as few samples as a function of n and epsilon. And the answer we get is that linear and n, in particular n over epsilon squared samples, actually suffice to distinguish between these 2 cases. So is the main result clear to everyone? Okay, thanks. So I'm not going to focus on the dependence on the error parameter epsilon for the rest of this talk. I'm just going to set that to a constant, and I'm only going to be focusing on sample complexity as a function of the dimension. So the first thing you might think is, well, 6 slides ago, I said that n should be a big number. Think of n as going to infinity, right? So we're in high dimension. So is this result actually impressive? So when you think about convexity in high dimensions, there's a bunch of other algorithmic tasks you can consider. And let's look at the sample complexity of this testing truncation vis-a-vis those tasks. Yeah.
Sorry, I have a question. Did you say distinguish always or distinguish with high probability?
Great question. So this is with high probability, with probability 9
Okay,
times
okay.
constant probability.
Okay.
Yeah, thanks. Yeah, no, that's a good point. You might get unlucky and get like a bad set of samples, so you need some amount of failure probability. Great. So so let me convince you that this linear in n sample complexity is actually interesting or impressive. And to see this, well, let's put down an x-axis where you're looking at sample complexity, and this testing truncation sits over here with linear sample complexity. Another natural algorithmic task to do with convexity and the Gaussian distribution is learning a convex set. So you're getting labeled samples. So you get a draw from the Gaussian distribution, and you're told whether this draw is in the set or not in the set. So it's labeled. And you want to output an approximator to the convex set. And this problem requires n to the root n samples, right? Another natural task with convexity and the Gaussian distribution is to test convexity. So you're again getting labeled samples, and you want to figure out if a set is convex or if it's far from convex. And this task, again, the best known algorithm has n to the root n, requires essentially exponential number of samples. And finally, one last task that people have been studying over the past 5 years is estimation. So you're getting samples from the truncated distribution, and you want to estimate the mean and covariance matrix of the Gaussian distribution. So these are some natural tasks, and this testing truncation problem is significantly easier. It has linear in n sample complexity as opposed to all of these other tasks, which essentially require 2 to the root n samples. And I've colored some of these boxes blue and some of them yellow. And that's because in the learning and testing problems, you're getting information about points which are in the set as well as not in the set. Whereas in this testing truncation and in this estimation problems, you're only getting samples from within the set. You're conditioning the Gaussian distribution on the set. So there's some distinction over here as well. So in some sense, this testing truncation is closer to this estimation problem.
Hey,
Okay, so-
Shivam, quick question. These are upper bounds only, or are they known to be tight?
So for learning, it's known to be tight. For testing, in terms of sample complexity, it is tight. But if you had query access, so if you could pick the points you're querying, then it's not known.
Got it. Thanks.
Yeah, and for the estimation, it's known to be tight. Good question. Thanks, Sean. Right. Great. So so there's a stark gap, 2 to the root n versus linear in n sample. So that's already kind of interesting. And we actually obtained results for some more classes of functions besides just truncation by convex sets. We can actually handle mixtures of symmetric convex sets. So let's say, all 11 participants on this call have a symmetric convex set, and every time someone wants a sample, we fight amongst ourselves to pick one of our symmetric convex sets, and we give them a sample from it. So we can handle this, harder version of the problem, but for a slightly restricted class of convex sets, namely symmetric convex sets, with the same amount of sample complexity. And we can also handle truncation by half spaces or linear threshold functions with square root n sample complexity. So half space is, again, a very simple class of objects, and maybe the first convex set we think of when we think of convex sets. You could do this with square root n samples. And in addition to upper bounds, we also get lower bounds, which show that, for convex truncation, you need linear in n samples. Again, same for the mixture for truncation by mixtures of symmetric convex sets, and also up to a logarithmic factor for truncation by half spaces. So all our results are either tight or essentially tight. And for the rest of this talk, I'm only going to focus on the first item, which is testing convex truncation. I'm not going to talk much about the lower bound, so let me just say one quick sentence about it. The lower bound is information theoretic, and it kind of boils down to a problem in random matrix theory. So it's kind of a nice clean connection, and it's not very difficult, but it's a little technical. So for the rest of this talk, I'm just going to focus on testing convex truncation, and I'm going to essentially sketch the whole algorithm and its analysis for the next 35 minutes. Yeah. Any questions so far? Okay. Right. So for the rest of this talk, the outline is going to be as follows. I'm first going to talk about something that's going to seem slightly like completely disjointed from everything so far, which is this notion of influence for convex sets. After going over this notion of influence, I'll tell you how we use it to distinguish truncation by reasonable convex sets, and then finally we'll finish off by handling all convex truncations. So let's get started with this influences for convex sets. And in order to motivate this, we're going to switch settings completely and talk about monotone Boolean functions. So the Boolean function is just a function that takes in a string of bits, zeros and ones, and outputs either 0 or 1. And a function is monotone if when you flip an input bit from 0 to 1, the value of the function does not decrease. So if it's 0, it stays either 0 becomes 1. If it's a 1, it stays at 1. And these are very natural, very simple objects that show up everywhere in combinatorics and theoretical computer science, right? And they're super well studied. Like we know a lot about their analytic structure. We know about density increment results, learnability. We know things like correlation inequalities for these functions. But you can ask these exact same questions about convex sets as well, right? So you can ask about the analytic structure of convex sets. Obviously, you replace the uniform distribution with the Gaussian distribution, replace the Fourier basis with the Hermite basis. You can ask about learnability. You can ask about correlation inequalities. And as kind of this slide suggests, there's an interesting analogy between the setting of monotone Boolean functions and convex sets of a Gaussian space. Like the results are often very similar, even though the proof techniques are often very different. And so there's this emerging analogy between these two, very different settings. And I'm going to shamelessly plug in some of my previous work with Rocco and Anindya, which introduced the notion of influence for convex sets. So in 2022, we introduced this notion of influence for convex sets. But in order to tell you what that is, I should first tell you what the usual notion of influence for monotone Boolean functions is. So given a Boolean function, you can think of it as a voting rule that takes in n people's votes and outputs either 0 or 1. So it's a two-party election. There's either candidate 0 or candidate 1, and the function just tells you who wins the election after n people have cast their votes. And the influence of a coordinate informally just captures how much the function depends on that coordinate. So in other words, it's the probability that when you draw a point uniformly at random from the Boolean hypercube, the value of the function at that point differs from the value of the function at the point obtained by flipping the ith bit. This is the influence of the ith variable, the ith coordinate on the function f. And there's been a long line of really beautiful work by the computer science and combinatorics communities on this that kind of centers on this notion of influence. And so just to give some examples, maybe the simplest Boolean function you think of is the Boolean dictatorship. So it's just a projection onto one of the coordinates. And the influence of that coordinate is going to be 1. So every time you flip that coordinate, the value of the function changes. And every other coordinate has influence 0. Another natural Boolean function is the majority function, which outputs 1 if at least half of the input bits are 1s. And the influence of any coordinate on the majority function is going to be 1 over root n, right? It's going to be the number of points in the middle layer of the Boolean hypercube. So divided by 2 to the n. So it's just by Stirling's formula, you'll get that this is 1 over root n. And finally, another extremal Boolean function is the tribes function, which is the AND of a bunch of ORs, and each OR is a tribe. And if you want to work out the influence for this, it's a calculation, but it's not too difficult. You'll see that the influence of each coordinate is log n over n, right? And so coming back to this notion of influence, it captures how much a function depends on a coordinate. And we want an analogous notion for convex sets of a Gaussian space. So we want to capture how much a convex set depends on a particular direction, but there's no canonical choice of directions in our end. You could ask for the influence of any direction on a convex set. So here's what Anindya, Rocco, and I did in 2022. Let's say you're interested in the influence of the first coordinate direction, which I'm denoting by this horizontal line, the direction E1. And here's a convex set K. What we propose is you take the set K and you stretch it out by a little bit along that direction. So you apply the linear transformation, which dilates the set by a factor of 1 plus delta, but only in the first coordinate direction. Okay. And after you do this, you look at the change in volume. So you look at the change in Gaussian measure, and you see how quickly it grows. So we're defining the influence of this direction E1 as the limit, when delta goes to 0, of the volume of this dilated set minus the volume of the original set divided by delta. Okay, so it's just a derivative of the volume when you dilate along that direction. Okay, any questions? Does this picture make sense to everyone? Okay, it seems like there's no questions. I'm going to keep going. So here's a really simple, first question to ask about this notion of influence. Well, if in the Boolean setting, if the influence of the coordinate is 0, then the function is independent of that coordinate. Like flipping that coordinate never changes the value of the function. So does something similar hold over here? And you can indeed show that this is the case. So if you have influence 0 for some direction, then the membership in that set, in the set K, does not depend on that direction at all, right? And proving this is actually non-trivial. We end up using a result which characterizes the equality cases, so the Erhard-Borel inequality, if you know what that is. But this really easy statement in the Boolean setting has a non-trivial analog in the Gaussian convex setting. So already there's some differences, but indeed what you would expect does hold. So it is a cylinder in that direction. Another natural question is whether there's analogs of the Boolean functions that we know and love for the convex setting. So it turns out that we do indeed have analogs. The analog of dictatorship is just a slab oriented along some direction. And indeed, like when you dilate the slab along any other orthogonal direction, the influence will be 0. But when you dilate along that direction, the influence is a constant. Another function we saw was a majority function, which in some sense is the top half of the Boolean hypercube in terms of Hamming weight. And the analogous function of a Gaussian space is the ball, which you can think of as the inner half of Gaussian space. And indeed, the influences line up again. The influence of any direction on the Euclidean ball of Gaussian measure half, the L2 ball of Gaussian measure half, is 1 over root n, just like the influences of the majority function. And the third function we saw was the tribes function. And again, this is, the tribes is an and of roughly n ors. And the analogous thing to do here is to take the intersection of n orthogonal slabs. In other words, you just end up with the cube, or the L infinity ball of Gaussian measure half. Again, it's a calculation, but you can check that the influence of each direction, each coordinate direction on this cube is log n over n. So far, these two sanity checks pass through okay. We know what zero convex influence means, and we have analogs of Boolean functions for symmetric convex analogs of Boolean functions. But we showed that this analogy is actually significantly deeper. Like you can get analogs of the Poincare and Concolai lineal inequalities. You can get a quantitative correlation inequality similar to what Talleyrand obtained over the Boolean hypercube, and much more for the setting of convex sets of a Gaussian space. And there's many interesting questions which are still open for this new notion of influence. But coming back to distribution truncation, to testing distribution truncation, we're actually going to need this Poincare inequality, this Poincare type inequality for symmetric convex sets. So before I proceed, any questions so far? Any questions about this notion of influence?
The analog of KKL, is it exactly same that maximal influence is log n over n for non-zero, non-constant, variance separated delta. Is it same or
It's exactly that, but it's slightly quantitatively weaker. So the usual KKL says that if you've got a Boolean function of that's balanced, variance half, then there exists a coordinate of influence log n over n. And we can show that there exists a coordinate of influence square root log n divided by n. So it's 1 times square root log n. So if you could improve that square root, if you could improve that to log n as opposed to square root log n, that would be great if someone could do that, but we don't know how to do it. Yeah. Right. Okay, great. So let me tell you what this Poincare inequality is. So the Poincare inequality, this is maybe the most mathy slide on the whole doc. It just says the following, that if you've got a convex set in Rn, then the sum of the influences along n orthogonal directions is at least the in radius times the variance of the set. And by the in radius, I just mean the radius of the largest origin-centered ball that's contained in the set K. So let's try to make sense of this this inequality by looking at the left-hand side, right? So I've talked about the influences along a direction, but what does it mean to add up the influences along n orthogonal directions? So let's just remind ourselves of what the influence of a direction was. The influence of a direction, you're just stretching the set along that direction and seeing how quickly the volume of the Gaussian measure is changing. So if you're doing this over n orthogonal directions, you're just uniformly dilating the set. Again, you were applying a linear transformation, so this is indeed what's happening. And so the influence along n orthogonal direction, the sum of the influences of n orthogonal directions is just the rate of change of volume of the set under uniform dilation. And just for convenience, I'm going to write this as bold I of K, and I'll call this the total convex influence. Right? So the left-hand side of the Poincare inequality was just the total convex influence, which captures the rate of change of volume when you dilate the whole set. And so the Poincare inequality was just saying that the total influence is at least the in radius times the variance of the set. And this is not too hard to prove. So here's a set K. Here's a ball of radius R in, which is the in radius. When you dilate it, you get this slightly bigger set. And I've written down the left-hand side of the Poincare inequality in the bottom. So it's just the rate of change. It's this limit. And well, if K contains a ball of radius R in, then delta K will contain a ball of radius delta Rn, right? Just convexity. So this total influence quantity on the left is at least the thing I've written down here. In particular, the volume of K plus delta K is at least the volume of K plus delta Rn times the ball of radius 1. So B1 just denotes the ball of radius 1. Right? So after this, it's just a little bit of calculus. So here I'm just copying what I had in the previous slide in the bottom. Well, let's do a change of variables. So let's multiply and divide by the in radius Rn. And now the thing on the right, this limit quantity is something we all know. It's just the Gaussian surface area. So the influence of the set K is at least the in radius times the Gaussian surface area. And now once you have this inequality, you just use standard bounds on Gaussian isoperimetry to show that this is at least the in radius times the variance. By variance, I just mean volume times 1 minus the volume. Okay, so this easy Poincare inequality does indeed have an easy proof. You're just kind of appealing to known bounds on Gaussian isoperimetry. Right? Did this make sense to everyone? Okay, great. So just to summarize what we need on convex influences, the influence just captures the change in measure under dilations. And we will need this Poincare inequality, which relates the total influence to the in radius times the variance. Right? That's all we're going to need from this section. So I'm just going to rewrite this as follows. I'm going to rewrite this by dividing both sides by the volume of the set K. So the normalized influence, the influence normalized by the volume, is at least the in radius times 1 minus the volume. That's all this Poincare inequality is saying. And this formulation would be slightly more useful in just like 4 slides. Right. So let's come back to the question that I started this talk with, which is this testing truncation problem. And first, I'm going to tell you how we do it for how we distinguish truncation by reasonable convex set. So what do I mean by reasonable? Well, here's an example of a reasonable convex set. In particular, this is, let me tell you what, in order to, so the upper bound we obtain is that given sample access to either the Gaussian distribution or the Gaussian conditioned on some reasonable convex set, linear and n samples suffice. And to formally tell you what reasonable means, by reasonable, I just mean that the set contains a ball of constant in radius. Right? So like when you're talking about the Poincare inequality, the in radius came up. And so we're just going to run with that notion. A convex set K is reasonable if it contains an origin-centered ball of radius 0.1. Just a really simple natural notion. So if you look at this picture, if your convex set contains a ball of non-trivial in radius, this really simple 2-dimensional picture suggests a really simple test, right? Like if you look at the samples on the left, there's a small number of outliers which are like really far away from the origin, and on the right, almost all of the samples are slightly clustered together. They're closer to the origin, and this suggests a natural test, which is to estimate the norm of your samples, right? So just to write this down more in words, just if you draw plots in 2 dimensions and look at them, the most natural test that at least we came up with was to estimate the squared norm of the samples. And this kind of lines up with this 2-dimensional picture, but it is possible that this 2-dimensional picture is misleading, right? That this low-dimensional intuition might be completely false in high dimensions. But this is where, the shameless plug from earlier for convex influences gets a socket that it fits right into. Because in our earlier paper, we showed that this normalized influence quantity is actually related to the squared norm of samples from a truncated distribution. So I'm going to call this an amazing fact, even though it's really just integration by parts. We showed that if you have any set K, then the squared norm of the samples drawn from the Gaussian conditioned on that set is equal to n minus the influence divided by the volume, right? So it's just n minus the total influence divided by the volume. And so this kind of suggests that maybe this hazy intuition is not completely wrong, right? Like we know that the influence is at least in radius times the volume. And so in radius times the variance. And so if we know that's big, then this is saying that the squared length of samples is going to be significantly smaller than n, right? So let's try to make sense of this. So when the distribution is just the Gaussian distribution, when no truncation has taken place, the squared norm of samples, well, this is just the sum of the expectation of xi squared. And each of these is 1 because it's a standard Gaussian. And so this is just n. And so when you have, and in the other case, when you're getting samples from the Gaussian conditioned on a convex set, the squared length of samples by this amazing fact is equal to n minus the normalized influence. And by the Poincare inequality, this is going to be at most n minus 0.9 times the in radius. Again, if you remember, I said that epsilon is 0.1. We're going to fix the epsilon in the talk to be like 0.1 or something. And so the convex set has measure at most 0.9. And so you get this, right? And because the set is reasonable, it contains a ball of radius at least 0.1. This is at most n minus 0.001. In fact, n minus 0.009, n minus 0.009, but yeah. All that matters is that it differs by a constant from the untruncated setting when no truncation has taken place. Does this make sense to you?
Sorry, can I have a question? A very quick question. Why the 0.9 turns out to be 0.01?
It should be 0.09, but it's because the in radius of the set is at least 0.1.
I see, thank you. And also because we condition the Gaussian distribution on some subset, so why the expectation of the radius actually decrease?
What is expectation of a radius? Sorry, what do you mean?
Sorry. Why the expectation of the x squared decrease if we don't
Okay, so,
condition?
sorry.
Yeah. So
We're-
previously,
Uh-huh.
yeah, previously the expectation is just n, but if we condition something on set k, then the expectation is less than n. Why we have this decrease?
Great. So it's not true if you condition on any set. Like imagine a set that's like very far away from the origin, and the expectation of squared length can go up, right? But if your set K is convex and it contains an origin-centered ball of radius 0.1, then it decreases. That's what we're saying here. Does that make sense?
Yeah, that makes sense. Very sense. Thank you very much.
Okay. Yeah. So again, we're using the assumption that your set K is convex and the fact that it contains a ball of radius 0.1 over here.
Thank you.
So this really simple test of estimating the squared length of samples differs by a constant in these two settings. And so let's use this, right? Like these two, this statistic differs by 0.01 between the truncated and untruncated settings. And so Chebyshev's inequality, your Markov-Chebyshev, should let us call it a day, right? Just estimate this statistic to constant accuracy and you're done. But there's a slight issue over here, which is that in order to use Chebyshev's inequality, you need the variance of this statistic to be the same in both the truncated and untruncated settings, right? And so let's actually see what the variance is. So the variance of the squared norm of samples in the untruncated setting, well, this is just the variance of draw from the chi-squared distribution. And you could, it's a one-line calculation, but if you're like me, you pull up Wikipedia, and then this is linear in n, so it's 3n. So in the untruncated setting, the variance of the statistic is 3n. But in the truncated setting, well, how do you actually compute the variance? All you know is that the set K is convex and contains a ball of radius 0.1. But at least we were not able to reasonably obtain a linear in n upper bound by like opening up this expression and trying to do some calculations. And since we failed, we actually went looking in the literature and we found a big hammer. And the big hammer was the Braskamp-Lieb inequality. So I'm going to really quickly remind everyone what this is. The full statement is significantly more powerful than what I've written down. But a consequence of the Braskamp-Lieb inequality is the following. It says that if you have a convex set K, then the variance of any differentiable function when you're getting samples from the set K is at most the expectation of the square norm of the gradient of that function with respect to the truncated distribution again, right? And so in the previous slide, I was talking about taking f as I was talking about the test function as the square norm of samples. And so when you plug f of x equal to the squared, sum of xi squared, you get exactly the variance of this on the left-hand side of this consequence. And on the right-hand side, you will get, well, the gradient of f is going to be 4 times the vector x. So the norm is just going to be, well, the gradient of f is going to be 2 times the vector x. And so the norm squared is going to be 4 times the norm of x. So coming back to this variance calculation, in the untruncated setting, the variance was linear in n, 3n. And in the truncated setting, Braskamp-Lieb tells us that this is at most 4 times the expected squared length. And using a Poincare inequality again, this is at most n. It's n minus something, but it's at most n. And in particular, the variance in the untruncated and truncated settings is comparable up to a constant factor. And so this lets us actually distinguish between the truncated and untruncated settings using linear and n samples, right? Just Chebyshev's inequality says that you should estimate the squared length of samples up to constant accuracy. And the probability of getting a false positive is going to be, whatever constant you want, as long as you have linear and n samples. Right, so let me now quickly tell you how to distinguish unreasonable truncation. So all sorts of all convex truncations. And the idea is really simple. So here's the main theorem that we prove in our paper. Given IID sample access to either the Gaussian or the Gaussian conditioned on some unknown convex set of volume at most 0.9, linear and n samples suffice. And the proof hinges on the following idea. You just consider two cases depending on whether K is reasonable or not. So let's set up a decision tree. So if K is reasonable, or in other words, if it contains a ball of in radius 1, we just do the thing we did earlier. We estimate the squared length of samples, and you distinguish using Chebyshev. So in other words, you're asking if this squared length of samples is at most n minus 0.001. And if it is the case, then you say that it's truncated. So let's consider the other case when the set K does not contain a ball of radius 0.1. So if it doesn't contain a ball of radius 0.1, this means that there exists some point at distance 0.1, which is not in the set K. And there's going to be two cases, two subcases. Well, let's say that the point it doesn't contain is the point on the x-axis given by 0.1, 0. And just by the separating hyperplane theorem, you know that there's some hyperplane that separates this point in the set K, right? And let's say that this is the hyperplane, and I'm rotating. It's a bit of a cartoon. It's in 2 dimensions, but hopefully it's fine. And so you know that this hyperplane separates this point from the set K. So in other words, K lies either completely to the left of this hyperplane or to the right. Right? So let's consider the case when it lies on the right. So the set K looks something like this. So it doesn't contain a ball of radius 0.1. But if the set is far away from the origin, there's a very natural test. You just estimate the center of mass. And this is going to be, non-trivially far from it's going to be non-trivially far from 0. And indeed, when there was no truncation, the center of mass is at the origin. So the squared length of the center of mass is, it's going to be very close to 0. So in this case, you ask if the center of mass is, at most 0.05 or whatever. And if it's not the case, then you can safely say that it's truncated, right? And if it is indeed the case that it's, really close to the origin, well, in this case, you might actually be a set that looks like this. So again, coming back to the 2-dimensional picture, here's the separating hyperplane, and let's say you lie to the left of it. Your set might actually be a very thin, very small set that's, whose center of mass is exactly at the origin. I'm kind of depicting it with this really thin slab over here. And in this case, we actually have to do a good amount of work to show that the convex influence-based test actually succeeds. So in this case, when your center of mass is really close to the origin, we kind of have to rely on a quantitative Braskamp-Lieb inequality to show that this other test actually succeeds. And this is actually bulk of the technical part of the paper. But just to keep things accessible and also interest of time, I'm not going to go over this part. But indeed, everything turns out to be okay, again, because of convex influences. So just to summarize, you can distinguish distribution truncation by convex sets using these two statistics, the squared length of samples and the center of mass based test. I didn't tell you how to estimate the center of mass, but there's a nice algorithm due to Sam Hopkins that allows us to do this. For the squared length of samples based test, the statistic will differ by a constant between the truncated and untruncated settings. And this is a consequence of this Poincare inequality and this Braskamp-Lieb stuff. And finally, you can just distinguish using Chebyshev's inequality. So Braskamp-Lieb gives you that the gap in the means is comparable to the standard deviation of the estimators. Right, so that's a very quick recap of everything I talked about. And so just to summarize, we get efficient distinguishers for different classes of truncations. Not only are these distinguishers efficient from a sample complexity point of view, but also from a computational point of view. So they're all like polynomial time distinguishers. So the runtime is also great. And we have matching information theoretic lower bounds for these different classes of truncations. And so there's some follow-up work that I've been doing to this paper. So convex sets are great, but another class of functions you might want to distinguish is polynomial threshold functions, which are possibly non-convex. So polynomial threshold function is just an indicator of it's just the sign of a polynomial. So a degree D polynomial threshold function is the indicator of a degree D polynomial P being bigger than 0. And in work that we're typing up right now, we can show that you can distinguish polynomial threshold function truncation over hypercontractive distributions. So this includes the Boolean hypercube, this includes Gaussian space. It's a broad class of distributions, and it's a broad class of truncations as well. It's convex as well as non-convex. And in another paper I've been working on, we consider the problem of testing junta truncation over the Boolean hypercube. So junta is just a function that depends on a small number of variables. Again, a very natural and very well-studied class of functions. So there's been some follow-up work. And something that I would really like to see is if people think about testing distribution truncation for other classes, either classes which people in computer science care about, or other distributions coming from probability and geometry. And that's all I have. I think I'm 2 minutes over time, but thank you all for listening.
Thank you, Shivam, very much. Any questions?
Yeah, I have a question. So do you know a priori what the in radius is?
Sorry?
Like how do you know? Are you given what the in radius is? You said the in radius is small.
No.
So how do you test that part?
So you run both estimators, and in the
Okay.
analysis, you can show that one of them will succeed by following that flowchart.
I see.
Yeah.
Okay.
I think Haonan has question. Haonan?
Hi, yes. Thank you very nice for the very nice talk. So in this nice picture, summarizing the similarity between the Boolean function in the Hamming cube and the convex functions in the Gaussian space. Do you have some junta type theorem in the Gaussian picture?
That's an awesome question. So let me see if I can jump back to that slide. So we don't have a junta theorem, and that would be amazing. Like I would really like to see a junta theorem. So we have all of these results, and we have like a weak consequence of Friedgood's junta theorem, but we don't quite have Friedgood's junta theorem. And in fact, we don't know how to prove a junta theorem. So here's a really simple one-dimensional problem that I don't know the answer to. So in the Boolean setting, suppose you have a function f, and the influence of the first coordinate is like epsilon. Then you can show that you're epsilon close to a function which doesn't depend on the first coordinate. But the analog of that in the convex setting, I don't know how to prove. So if you have a convex set and the influence of the first coordinate direction is at most epsilon, then are you epsilon close to a cylinder? So I had this thing saying that, if the influence is 0, then you are indeed a cylinder. But can you prove a stability version of this simple fact, this not so simple fact, which says that you're epsilon close to a cylinder? And by close, I mean in L1 distance or in total variation distance. And this is maybe the first step towards proving a junta theorem, but we don't know how to do this. Ronan Eldon knows how to show this with respect to Wasserstein distance. So he can show that if your influence is at most 0.1, then you're 0.2 close to a cylinder in Wasserstein distance, but it doesn't imply it for L1 distance. But that's a great question. Yeah.
Okay, so apart from this junta theorem for the influence, say that for the junta type theorem for degree, and do we know anything about this? If a polynomial in this, yes, now a polynomial is in this air-made basis is of low degree, then it is close to some junta.
That's a good question. So this notion of influence, the influence might be negative for the polynomial. So the influence is only non-negative if you have a convex set which contains the origin. So this notion of influence seems very tied to convexity. We can't say anything about polynomial threshold functions.
Okay, thank you.
But I think there's a paper called Geometric Influences by Keller, Mosel, and Sen, and I think their stuff might be saying something about polynomials, but I'm not sure. Yeah.
Any other questions?
I just have a very simple question. So in general, why we are interested in if the distribution is truncate or not?
Oh, if this distribution is truncated or not?
Yeah. Why we want to distinguish it?
Awesome. So you're asking why you should even care about this. So people try doing, things with truncated distributions, right? Like as an example, this paper in the bottom right tries to estimate the mean and covariance from truncated distributions, and there's a lot of work on truncated. There's a lot of algorithms for truncated distributions, but it's arguably much more natural to before running those algorithms, which have high sample complexity or runtime, you might want to even know if you need to run that algorithm, right? Like before you try doing any kind of estimation or inference on a truncated distribution, you want to figure out if your distribution is truncated in the first place, right?
I see.
Yeah.
So if the distribution is truncated, then we can use some maybe simpler algorithm to estimate something.
Exactly. Yeah. Like there's a whole body of work on truncated statistics, and it seems like it's very natural to want to know if you even need to use that machinery in the first place, right?
Thank you very much. By the way, is in real practice because in real practice we only have finite number of samples, so is every distribution is actually truncated in real application?
Yeah, that's a good. You're saying that. Yeah, I'm not quite. I mean, if you're dealing with high dimensional distributions, you have like. You can get a large number of samples. So I don't think I have a satisfying answer to that question, but yeah.
Thank you very much.
Yeah, maybe a comment and a question. So I guess beyond just the utility of testing truncation in order to run later algorithms, I guess in natural sciences, truncation is often called censoring, like you had in those book titles. And so if you want to know more about that, it is a very serious question in a lot of experimental studies about whether or not there's some unknown conditioning happening on what you expect the distribution to be. So it really appears everywhere in experimental sciences. And then I was just wondering, this is probably a stupid question, but if I had a disjoint, if I was conditioning or truncating on a disjoint union of convex sets, let's just say a disjoint union of two convex sets, not necessarily centered, right? Just floating out in space. I should be able to test this.
Disjoint union of two convex sets.
Or is this already hard?
I don't know. So you certainly cannot handle a mixture of convex sets. But I don't know if you can do, like, off the top of my head, I'm not sure. Like for the first picture that comes in mind is like half spaces facing opposite ways. That seems doable. But I'm not actually, yeah. How would you maybe I'm not seeing how to do that with the two tests that I have.
I see.
If you have half spaces facing the opposite way, the center of mass still is the origin. And the squared length of samples can be, you pick the parameter so it's linear in n. So I'm not convinced. I'm not sure. I'll have to think about it.
I mean, I guess that example is obviously a bimodal distribution, and so
yeah. So there's a different test. You're right. Yeah.
Okay, but it doesn't. This is not something you've thought about. It doesn't seem to fit in this framework.
I have not thought about it, and it's a good question. Like it'd be nice to say something about, disjoint unions of convex sets. Yeah.
Got it. Thank you.
Yeah. Actually, Joe, does the Swiss cheese example make that hard?
I think that's the complement, right? You're conditioning on.
Yeah, you're right. Yeah. Shabarish, yeah.
Shabarish has a question.
Yes. So what are the barriers to doing this for distributions other than the normal distribution?
That's awesome. So we haven't thought too hard. Like it'd be great to do this for, log concave distributions. And I think this notion of influence also makes some sense. I've thought a little bit, but we haven't like finished writing it up or thinking too hard. Yeah. But
Okay.
It'd be great if people thought about this for different distributions. Yeah.
Okay, I think we asked lots of questions, so let's thank the speaker again.
Thank you all for listening.
I will stop